You think you live in a stable, predictable universe, but today you're going to find out how wrong that is. From a cosmos that might switch off reality without warning, to stars that can erase whole biospheres in seconds, to dark energy that could one day rip atoms apart, to creepy game theory reasons why the sky is silent and every advanced civilization might be hiding in terror. In this video, we're going to walk through the most disturbing scientific ideas that real physicists argue about. The ones that say the universe is not safe, not stable, and definitely not built with you in mind. You go to sleep in a normal universe, same bed, same room, same physics, and there is a tiny, uncomfortable fact you will never feel. The basic state of empty space itself might not be truly stable. This idea is called vacuum decay. It is not a movie plot. It is a direct consequence of the equations we use to describe particles and forces. According to the standard model of particle physics, space is not really empty. It is filled by fields. One of them is the Higgs field, the thing that gives particles their mass. In 2012, experiments at the Large Hadron Collider measured the Higgs particle to be about 125 billion electron volts in mass. And when you combine that with the measured mass of the top quark, you get a disturbing result. Our universe looks like it might be in a metastable state. Metastable means this: our current vacuum, the background state of all these fields, is not the absolute lowest possible energy. It is stable on human and stellar timescales, but not guaranteed to be stable forever. In quantum mechanics, even a state that is not the deepest possible can hang around for an extremely long time, but it always has a non-zero chance to change. So what does it mean for the vacuum to change? In quantum field theory, there is some deeper, lower energy configuration of the Higgs field and possibly other fields. Our universe is sitting in a higher energy configuration. Because of quantum tunneling, there is a tiny chance that at some random point in space, the fields jump to that lower energy state in a small region. That event would create a bubble of true vacuum surrounded by our current false vacuum. Inside that bubble, the numbers that define the universe are different. The Higgs field takes a different value, which means particle masses change. The strengths of the forces can change. The rules that allow atoms and stable matter to exist may no longer hold. You do not get a fireball or a dramatic visual effect. You get a region of space-time where the basic constants are not the ones you were built for. And the story gets worse. That bubble does not stay small. The lower energy state is more favourable, so the bubble wall is driven outward. In all realistic calculations, the bubble expands at very close to the speed of light. That means there is no early warning. You cannot see it coming because any light that would carry the information is travelling at the same speed as the bubble wall. From the point of view of an observer, one moment everything is normal, the next moment the local laws of physics are different, and stable structures like atoms and molecules are no longer possible. There is no pain, no drama, no time to react. There is simply no continuation of your physical structure into the new vacuum. It is not a normal disaster. It is the end of the specific version of physics that allows you and planets and stars to exist at all. This sounds like a fringe idea, so why do serious scientists talk about it? Because it drops out of the same standard model that successfully predicts particle interactions in accelerators and matches countless experiments. When theorists take the measured Higgs mass and top quark mass and run them through renormalization calculations up to extremely high energies, they can map out regions of parameter space. One region corresponds to a fully stable vacuum, another to a metastable vacuum, and another to an unstable one. With our current best measurements, the point representing our universe falls right on the border between stable and metastable, slightly on the metastable side, though the error bars are still large. This is why you will see those famous plots in papers, with axes labelled by Higgs mass and top quark mass, and coloured zones for spility, metastability, and instability. We are not far inside the safe region, we are close to the line. That alone is unsettling because there is no clear reason for nature to pick values that sit right on that knife edge. Now the question you care about, is there any realistic chance this happens soon? The good news is, according to most calculations, the expected lifetime of our current vacuum is insanely long. When people estimate the tunneling rate for our parameters, they get a lifetime that is not just longer than the age of the universe, but longer than the time it would take for all the stars to burn out and all black holes to evaporate. You're talking about numbers like 10 to the power of 100 years or more, so large that for any time period that matters to humans or even to galaxies, the risk is effectively zero. So are we completely safe then? Is this just academic? Physically, on any reasonable timescale, yes, you're not going to lose sleep over a vacuum decay bubble. But conceptually, it is not harmless at all. It tells you something stunned and disturbing about how finely tuned our universe seems to be. Our best tested theory does not lock us into a perfectly stable vacuum. It leaves us hovering near the boundary where the universe is only metastable, where the underlying fields are in a state that works for now but is not guaranteed forever. We do not know why the Higgs mass has exactly this value. We do not know if there is new physics that will eventually show up and either stabilize the vacuum completely or push us further into the dangerous region. Right now, we just see that the numbers we measure, combined with the equations we trust, put us in a strange position, apparently safe for absurdly long times, but not fundamentally secure. There is a deeper psychological hit here. It means the basic fabric of reality is not something you can assume is absolute. The fact that atoms exist, that chemistry works, that stars shine, may depend on parameters that could, in principle, jump to a different set that supports none of this. The universe is not a fixed stage, it is a system whose ground state might not even be the one we are currently in. And if the vacuum itself might one day change under our feet, even if that day is unimaginably far away, it raises another question that is just as chilling. What if the universe does not end in a sudden flash, but in a slow, drawn-out fade? A future where nothing explodes, nothing flips, but everything simply runs down into permanent, featureless silence. This is the universe's slowest jump scare. Nothing explodes, everything just stops. You hear about big, dramatic endings, giant collisions, fireballs, shockwaves, but the most likely fate our best physics points to is much quieter. The universe just gets old and tired and smooth until there is nothing left that can actually happen in it. That story starts with one idea you have to take seriously: entropy. Entropy is basically a measure of how spread out and disordered things are. The second law of thermodynamics says, in an isolated system, entropy tends to increase. You never see all the air in your room suddenly gather into one corner on its own, because that would be a big drop in entropy. What you do see is perfume spreading out, hot coffee cooling down, things mixing and equalizing. Now scale that up. The universe, as far as we can tell, is the ultimate isolated system. There is nothing outside it to dump heat into, nowhere to send its waste energy. So over time, entropy for the whole universe goes up. When entropy goes up, energy does not disappear, but it becomes less useful. Useful energy is energy with a difference, a contrast, something you can exploit, like a hot region next to a cold region, high pressure next to low pressure. Engines, storms, living cells, your own brain, they all feed on those differences. The second law says those differences will keep getting erased. Energy spreads out, becomes more uniform, harder to use. Step one of the big freeze is simple. The universe slowly loses its ability to do anything interesting because the contrasts get washed away. So what does that actually look like in space? Not just in equations, but in real objects like stars and galaxies. Right now, the universe is still full of bright young stars. But if you look at the data, you see a clear trend. Astronomers measure the star formation rate across cosmic history by looking at galaxies at different distances, which means different times in the past. What they find is this: the universe used to form stars much more rapidly. The peak was roughly 10 billion years ago. Since then, the star formation rate has dropped. Galaxies today, including the Milky Way, are less active. They are living on the leftovers. Why? Because gas, the raw material for stars, does not stay in giant cold clouds forever. Supernovae blow it out, black holes heat it, some of it gets locked up in long-lived stars and never comes back out as gas. Over billions of years, the easy fuel is used up or trapped. As time goes on, fewer massive bright stars are born. The population shifts towards smaller, cooler red dwarfs that burn their fuel extremely slowly. In the far future, new star formation grinds almost to a halt. You are left with a universe populated by old stars, stellar corpses, and a very long, dim tail of red dwarfs taking their time to die. You might think, okay, but red dwarfs can live for trillions of years. Doesn't that mean the universe stays lively for a long time? Yes, but lively gets weaker and weaker. After enough time, even those red dwarfs will finally exhaust their fuel. There will be a last generation of stars and then no new ones to replace them. At that point, starlight as we know it is basically over. What comes after the last star goes out? Once normal stars are gone, the universe enters a very different phase. The main visible players are stellar remnants, white dwarfs, neutron stars, and black holes. White dwarfs slowly cool and fade. Neutron stars spin down and become cold, dark lumps. Some of them may collide and merge, but even those events become rare as everything spreads out. Gravity still clumps matter, but over insanely long times, even stable orbits can be disturbed, and many objects fall into the central black holes of their galaxies. Black holes then take over as the dominant massive objects. Supermassive black holes, millions or billions of times the mass of the Sun, sit at the centres of dead galaxies. For a while, those are the last big engines of drama, swallowing stars and gas that wander too close. But even black holes are not eternal if you include quantum effects. Stephen Hawking showed that black holes should slowly lose mass by emitting radiation, a process called Hawking radiation. The smaller the black hole, the faster it evaporates. But even for big ones, the key point is the clock is ticking. The timescales here are hard to even say out loud. A black hole with the mass of a star takes something like a number of years written as a 1 followed by 60 or more zeros to evaporate. A supermassive black hole can take a 1 followed by around 100 zeros or more. That is far beyond the current age of the universe. But given enough time, it happens. One by one, over a ridiculous stretch of future, black holes radiate their mass away as faint particles and photons, and in their final moments, they end in a short bright burst, then nothing. After that, what is left to actually do anything? When almost all the mass has been locked into black holes and those black holes have evaporated, the universe is stripped down to the bare minimum, a very thin gas of low-energy photons, neutrinos, and maybe some extremely light particles drifting through an ever-expanding space. There are no stars, no planets, no solid structures, just radiation and a few particles, spread over volumes so huge that the density is effectively zero for any practical purpose. This is where the phrase heat death comes in. It does not mean everything is burning, it means the opposite. Everything is in thermal equilibrium. Temperatures everywhere are almost the same, extremely close to absolute zero, but not quite. With no temperature differences, you cannot run an engine. You cannot extract work. You cannot drive chemical reactions in any organized way. Information processing, which is what your brain and any computer does, also depends on energy differences and the ability to erase and write states. In heat death, those options are gone. The cosmos is still there, but it has no built-in way to create new structure or complexity. In that state, the laws of physics still hold, but they are boring. Particles occasionally interact, but those interactions do not build anything long-lasting or complex. The universe has done its main work, and then it just coasts, forever, as a thin, cold, almost featureless sea. Here is the part that hits you personally. You live in a ridiculously special time. Right now, the universe still has huge temperature contrasts, bright hot stars in cold space, dense galaxies in a mostly empty cosmos, planets with internal heat next to freezing outer space. All of biology, all of technology, all of human history sits inside this narrow, high-energy window. The early universe was too hot and simple. The far future will be too cold and uniform. Most of cosmic time by far is not like this. It is just nothing much happening. So when you look up at the night sky and see a few thousand stars, you are not seeing a permanent feature. You're seeing the afterglow of a brief active phase before the universe runs down. The Big Freeze is not a sudden disaster. It is the slow loss of every tool the universe has to make new things. And as bleak as that sounds, there is an even harsher possibility on the table. What if the universe does not just fade into a cold stillness, but the expansion itself turns violent, and space stretches so fast that it rips apart galaxies, solar systems, even atoms? You're not ripped apart by gravity, you're ripped apart because gravity cannot keep up anymore. Space itself stretches so fast that nothing can hold together. Not galaxies, not solar systems, not even the atoms in your body. To understand how we even get to that point, you go back to what we learned in the late 1990s. Astronomers were measuring how fast the universe is expanding by looking at special exploding stars called type Ia supernovae. These things have nearly the same brightness every time they go off, so they work like standard candles. If you know how bright they really are, you can tell how far away they are by how faint they look. When two independent teams used them to map out distances and redshifts, they expected to see the expansion slowing down over time, because gravity should be pulling everything back together. What they actually found was the opposite. Distant supernovae were dimmer than expected. That meant they were farther away than they should be in a slowing universe. The only way to make the data fit was to accept that the expansion of the universe is speeding up, not slowing down. Something in the equations acts like a kind of negative pressure, a push built into empty space that makes the expansion accelerate. We gave it a plain name, dark energy, but it is controlling most of the total energy content of the universe. So the next question is, what kind of dark energy are we dealing with? Cosmologists describe it with a number called U, which is just a ratio, pressure divided by energy density. If W is equal to -1, the dark energy behaves like a simple cosmological constant, fixed energy built into space itself. In that case, the expansion accelerates, but in a steady way, you get something like the Big Freeze future. If W is less than -1, something really strange happens. That case is nicknamed phantom energy. When W drops below -1, the density of dark energy does not dilute as space grows, it actually increases. The more volume you have, the more dark energy you get. And that feedback loop drives the expansion faster and faster. This is where the big rip picture comes from. In a phantom energy universe, the expansion does not just keep accelerating smoothly, it races toward a kind of deadline in the future. As you move closer to that time, the repulsive effect of dark energy ramps up without bound. Structures held together by gravity or by other forces eventually cannot resist it. If you run the numbers for a specific example, where W is just a bit less than -1, you get a rough timeline. First, on very large scales, galaxy clusters lose the battle. The extra push from dark energy grows so strong that it overcomes the gravity tying clusters together. Galaxies that used to orbit in a cluster drift away from each other, each one sliding into its own bubble of space alone. Much later, the same thing happens inside galaxies. The Milky Way, Andromeda, all the stars that were bound together, get pulled apart. The expansion of space on those cylinders becomes stronger than the gravity that was holding the galaxy together. From the point of view of any one star, the rest of the galaxy seems to be racing away faster and faster. As you get closer to the final moment, the scale of destruction shrinks. At some point before the theoretical rip time, dark energy's repulsive effect becomes strong enough to unbind solar systems. Planets can no longer stay in orbit. They drift away from their stars as the expanding space between them overpowers the star's gravity. Closer still, the same process reaches down to planets and moons, tearing apart anything held together by gravity alone. And then, right near the end, it gets even more extreme. The tidal stretching from the accelerating expansion becomes strong enough to overwhelm the electromagnetic forces that hold atoms and molecules together. In the last tiny fraction of the timeline, even atoms cannot remain intact. The scale factor of the universe, the number that tells you how far apart things are, races to infinity in a finite amount of time. Some models with W just below -1 put this doomsday more than about 200 billion years in the future. That is far away, but it is not never. Now, before you relax and throw this into the pure story bin, here is the uncomfortable part. We do not actually know what it really is. We measure it using data from the cosmic microwave background, galaxy surveys, gravitational lensing, and those same kinds of supernova observations. The Planck satellite and other projects have pinned W down to be very close to -1. But very close is not the same as exactly. The best fits say something like consistent with -1 within some small error bars. Inside those error bars, there is room for W to be slightly greater than -1, or slightly less than -1. That means, from the point of view of current data, phantom energy is not ruled out. We cannot say the Big Rip definitely will happen, but we also cannot say the Big Rip definitely cannot happen. It is still on the menu of logically possible futures compatible with what we see. To make things more frustrating, even small differences in W matter a lot. A tiny shift below -1 that you could not feel locally in any experiment today completely changes the ultimate fate of the universe over hundreds of billions of years. So the real horror here is not that some specific Big Rip model is likely, in a betting sense. The real horror is that our best measurements of the thing that decides the long-term fate of everything are still too fuzzy to choose between radically different endings. With the same high-quality data set, you can tell a Big Freeze story, where galaxies slowly drift apart and stars fade, or a Big Rip story where the expansion eventually outmuscles every bond in nature and tears apart all structure. You are living in a universe where most of the energy is in a form we do not understand, pushing on space in a way we barely constrain, and that component will decide whether the cosmos coasts, rips, or maybe even reverses. Because there is another twist. If dark energy is not a fixed constant at all, but something that can evolve and even change sign, the universe does not have to end in a freeze or a rip. It could slam on the brakes, stop expanding, and fall back in on itself. What if the universe is secretly breaking, the expansion already slowing down, setting you up not for a slow freeze, but for a reverse Big Bang where everything ends in a crushing big crunch? For a long time, the story in cosmology was simple, at least on paper. There were two main endings. One, not enough matter. Dark energy acts like a constant push. Expansion goes on forever. Galaxies drift apart, stars burn out, and you get heat death. 2. Enough matter and the right kind of dark energy, gravity eventually wins. Expansion slows, stops, and then reverses. Once it turns around, everything that is now moving away starts falling back together. Galaxy clusters contract, galaxies move toward each other, distances shrink instead of grow, and over a very long time you end up with a big crunch, a kind of mirror image of the Big Bang. In that classic picture, the rule is straightforward. If gravity from all the matter and energy in the universe is strong enough and there is no eternal repulsive dark energy dominating forever, the universe cannot keep expanding. It has to decelerate, stall, and then collapse. If gravity is too weak, or dark energy is too persistent, expansion never stops. The problem is, those outcomes depend on two things that are extremely hard to measure precisely: the total amount of matter and energy, and the detailed behavior of dark energy over time. Then came the late 1990s. Type Ia supernovae were used as standard candles, and the data showed distant supernovae were dimmer than they should be in a decelerating universe. The conclusion was shocking at the time: the expansion is accelerating. Dark energy looked like a constant repulsive component built into space itself. That view won a Nobel Prize and locked the Big Freeze in as the default ending. But that neat picture is now showing cracks. In 2025, several teams went back to the supernova data and started asking, what if some of our assumptions are slightly off? One line of work looked at how the ages of the galaxies that host these supernovae can bias brightness measurements, then recalibrated the distances and combined them with independent data from galaxy clustering and the cosmic microwave background. Some of those reanalyses report something dramatic. Once you correct for those effects, the supernova data no longer clearly require an accelerating universe at the present time, and they fit better with models where dark energy changes with time instead of staying perfectly constant. A particularly strong claim comes from a group led by Youngwook Lee. They argue that after correcting for an age bias in supernova hosts, the best fit models say the universe has already entered a phase of decelerated expansion today, and that dark energy is evolving much faster than the standard model allows. In their analysis, the simple constant dark energy model, the classic cosmological constant, is ruled out with high statistical confidence. At the same time, large supernova catalogues and DESI survey data also hint that dark energy may be getting weaker over time, which naturally leads to slower expansion instead of endless speed up. These results are controversial, and not everyone agrees yet, but they open the door again to a universe that is not locked into a permanent acceleration. If dark energy is weakening or even changing character, gravity gains ground. So what kind of dark energy lets that happen? This is where ideas like quintessence come in. Instead of treating dark energy as a fixed number baked into space, you model it as a field, similar in spirit to the Higgs field, spread throughout the universe. That field carries energy. Depending on where it sits in its potential, its energy density can slowly roll down or even change sign. As it moves, its pressure and energy density change together, and the ratio between them, the parameter cosmologists call Luoi, is no longer exactly -1 and no longer constant in time. In simple terms, dark energy goes from being a rigid background to being a dynamical substance that can strengthen or weaken as the universe evolves. If that field slowly loses energy, the effective dark energy density drops. Its repulsive effect on the expansion fades. Gravity from matter starts to dominate again. In more extreme versions of these models, the dark energy term can even cross from positive to negative, so it stops acting like an anti-gravity and starts acting like extra gravity. At that point, you have a built-in cosmic doomsday. The same physics that once helped the universe speed up now helps pull everything back in. Expansion slows more and more, stops at some maximum size, and then flips into contraction. Once contraction starts, the process is not gentle. Over huge timescales, galaxy clusters that were drifting apart turn around and begin to fall toward each other. Galaxies merge more and more often. Large-scale structure gets denser. Because the universe is shrinking, background radiation heats up instead of cooling down. The average temperature of space begins to rise again. Densities increase, space-time curvature grows, and in the final stages, the entire observable region is driven toward extreme conditions, with energy densities and temperatures similar to what we think existed fractions of a second after the original Big Bang. From inside that universe, every distant galaxy you see today would, in the end, be on a trajectory into the same collapsing fate. That picture naturally leads to the cosmic reboot idea. If the universe can crunch, maybe it can bounce. There are models, often called cyclic or phoenix cosmologies, where the universe never really begins or ends once. It goes through repeated cycles. In each cycle, there is an expansion phase, then a slowdown, then a contraction, then a bounce that triggers the next expansion. The big crunch of one cycle becomes the starting point of the next Big Bang. Modern versions of these models use tools from high-energy physics and modified gravity to try to make that bounce mathematically consistent, instead of just hand-waving it. From your point of view, though, this does not make things friendlier. Whether or not there were previous cycles before ours, everything in our observable patch still heads into that future high-density state if a crunch happens. Your galaxy, your stars, your atoms all end up as part of whatever extreme state sits at the bounce. Any new expansion after that does not remember you or the Milky Way in any direct way. It is a fresh universe with new structures, even if it is connected by deep physics to the one that came before. This is why this whole topic genuinely unnerves cosmologists. Put all the options on the table and you see something uncomfortable. The fate of everything depends on tiny details of dark energy, on how that mysterious component of the universe changes with time. Slight shifts in how the field rolls, small differences in the behaviour of W decide whether the universe coasts into a cold big freeze, races into a big rip or breaks, turns around and plunges into a big crunch and possible reboot. The sign of the universe's long-term fate, expansion forever or eventual collapse, may already be fixed by numbers we've only measured to 1 or 2 decimal places. Right now, different data sets and analyses pull in different directions. Some still favour a nearly constant dark energy very close to a cosmological constant, which points to endless expansion. Newer reanalyses hint at weakening dark energy and real deceleration, which would make a future recollapse possible again. None of this is settled enough to call the final shot. But you are already living in a universe where 3 very different endings, freeze, rip or crunch and reboot, are all still allowed by the current error bars. And just when you think that at least this huge uncertainty is only about the far future and the largest scales, you run into something closer and more personal, the regions around black holes, where gravity is so strong that our best theories clash, and we are not even sure whether the universe keeps a memory of what happens there. There are places in the universe where what happens might literally vanish from reality's memory, and those places are around black holes. Start close to a typical stellar mass black hole, about 10 times the mass of the Sun. The gravity there is not just strong, it is uneven over the length of your body. Your feet are closer to the black hole than your head, so they feel a stronger pull. That difference is called a tidal force. Near a few times the event horizon of a 10 solar mass black hole, the difference in pull over 2 meters can be millions to hundreds of millions of times Earth's gravity. That is a tidal field in the range of about 1 million to 100 million G. At that level, your body is not just pulled down, it is stretched into a long, thin shape and ripped apart. This process has a dry name, spaghettification. The physics behind it is simple. Gravity falls off with distance, so if the gravity is extreme and the distance across your body matters, you get shredded. Now that is a small black hole. On the other end, we have monsters that we have actually seen. In 2019, the Event Horizon Telescope collaboration released the first direct image of a black hole, the supermassive one in the galaxy M87. It sits about 55 million light-years away and has a mass of around 6.5 billion suns. In 2022, the same project released an image of the black hole at the centre of our own galaxy, Sagittarius A, with a mass of about 4 million suns. We did not just guess those masses. In the Milky Way, astronomers tracked individual stars like the star called S2, whipping around an invisible point near the centre. By measuring their orbits, they could use the same gravity math that keeps satellites around Earth, just scaled up. And the only answer that fits is a compact object with millions of solar masses squeezed into a region smaller than our solar system. In M87, the apparent size of the dark shadow in the EHT image, combined with distance, gives a mass that matches independent estimates from the motions of gas and stars. These are not theoretical decorations, these are real measured objects. Around a supermassive black hole, the story is different again. The event horizon might be bigger than the orbit of Mercury. The tidal gradient at that radius is much gentler than around a small black hole. You could, in principle, cross the horizon of a giant black hole without being torn apart instantly. Locally, you might not feel anything special as you pass the point of no return. That contrast itself is disturbing. Small black holes kill you violently before you even reach the horizon. Giant ones let you fall in relatively calmly, but in both cases, once you cross that horizon, classical physics says you never come back. And that is where the deeper problem starts. In Einstein's general relativity, a black hole is just space-time curved so strongly that inside a certain radius, all possible paths lead further in. Anything that falls in, matter, light, your hard drive full of memories, is gone from the outside universe. From the outside point of view, the only things you can ever learn about what fell in are its total mass, its total electric charge, and its total spin. That is summed up in the phrase, black holes have no hair. Everything else about the details is erased from the outside description. Then you bring in quantum mechanics, and things clash. In the 1970s, Stephen Hawking showed that when you combine quantum fields with curved spacetime near a horizon, black holes should not be perfectly black. They should slowly emit radiation, now called Hawking radiation. It is almost like the vacuum near the horizon spits out pairs of particles, with one escaping to infinity and one falling in. To someone far away, the black hole looks like it has a temperature and glows very faintly. As it glows, it loses mass. That means a black hole has a finite lifetime. A black hole as massive as the Sun would need around 10 to the 67 years to fully evaporate. Supermassive ones run all the way up to lifetime between about 10 to the 68 and 10 to the power of 100 or more years. Here's the catch. Hawking's original calculation said this radiation is purely thermal, basically random, like heat coming off a hot object. That kind of radiation does not carry detailed information about what fell in. So if a black hole forms from some complicated object, lives for a long time, and then evaporates into thermal radiation, all the fine-grained information about the original state seems to vanish. But in quantum mechanics, that is not allowed. The evolution of a closed system is supposed to be reversible in principle. If you know the final quantum state perfectly, you should be able to work back to the initial state. You should never lose information. So now you have an information paradox. General relativity says the horizon hides everything except a few global numbers, and Hawking's calculation says the evaporation process gives back only random radiation. Quantum mechanics says the detailed information should survive somehow. Both theories are incredibly successful in their own domains, but put together in this extreme situation, they disagree. A huge amount of modern theoretical physics, from holography to the idea that the information is somehow stored on the horizon itself, is basically an attempt to fix this conflict without giving up the parts of either theory that already work. So far, there is no complete answer that everyone accepts. Now tie this back to the far future you heard about with the Big Freeze. After star formation ends, and after normal stars fade, black holes are expected to dominate the mass budget of the universe for a huge stretch of time. For trillions and trillions of years, they will quietly sit there, swallowing any stray matter, while the rest of the universe thins out. On truly ridiculous timescales, up to around 10 to the power of 100 years or more for the biggest ones, Hawking radiation slowly eats away at their mass too. The last phase of a black hole's life is the only really fast part. As it loses mass, its temperature rises, so it radiates faster, which makes it lose mass even faster. In the final moments, the power output spikes. For a tiny fraction of its lifetime, the evaporating black hole could outshine whole galaxies in high-energy radiation before winking out completely. In some models, the absolute last visible events in a dying universe are these brief flashes from the final black holes evaporating. After that, only thin, cold radiation remains. So here is the meta-horror. Black holes are not just places that crush matter. They are places where our deepest theories argue over something as basic as whether the universe remembers what happened there. From far away, all that character, all those specific histories, seem to be compressed into a few numbers and then maybe burned off as featureless heat. From the point of view of quantum mechanics, that should not be allowed, so something subtle and still unknown has to be happening at the edge or inside these objects. You live in a universe where regions of space-time exist that push our understanding so hard, we genuinely do not know if reality keeps a full record of events there or not. And even outside black holes, there are events that can wipe out entire biospheres in a heartbeat. Not by bending space-time, but by hitting a planet from across the galaxy with a beam of pure energy. Somewhere out there, A star can die so violently it erases an entire biosphere, and you would never see it coming until the damage is already done. Gamma-ray bursts are exactly that kind of event. They are not slow, they are not gentle, they are a few seconds of extreme power focused into a narrow beam. There are two main families. Long gamma-ray bursts come from the collapse of very massive stars, stars many times heavier than the Sun, that run out of fuel and fail as normal supernovae. Their cores collapse into a black hole or a neutron star, and jets punch out along the poles, blasting gamma rays out into space. Short gamma-ray bursts come from mergers of neutron stars, or a neutron star with a black hole. Two ultra-dense objects orbit each other, spiral in, collide, and again jets fire. In both cases, the numbers are extreme. In a timescale of seconds, sometimes less, a gamma-ray burst can release as much total energy as the Sun will emit in its entire 10 billion year lifetime. That total is calculated as if the energy went out evenly in all directions. In reality, it is concentrated in narrow beams, so if you're unlucky enough to be in the path of one of those beams, the intensity is even higher. You're not dealing with a slow climate shift, you're dealing with the sky turning into a hard radiation lamp. This is not speculation. We see these things all the time with space telescopes. Satellites like Swift and Fermi sit there, watching the high-energy sky, and they regularly pick up sudden spikes of gamma rays from random directions. They are so bright that for those few seconds a single burst can outshine its entire host galaxy in gamma rays. Astronomers then go and find the fading afterglow in X-rays, visible light and radio, and they trace it back to distant galaxies. Some of the most distant explosions we have ever seen are gamma-ray bursts, from a time when the universe was less than 1 billion years old. So the obvious question is, what happens if one of these points at you? The Earth is protected from a lot of space radiation by its atmosphere and magnetic field. Gamma rays themselves do not punch straight through to the ground in large numbers, they interact in the upper atmosphere. But if a strong gamma-ray burst went off within a few thousand light years, with its jet aimed more or less directly at Earth, the energy dumped into the atmosphere would be enough to cause serious damage. The high-energy photons would break apart molecules like nitrogen and oxygen, drive chemical reactions, and destroy a large fraction of the ozone layer. Ozone is what blocks most of the harmful ultraviolet light from the Sun. With that shield weakened or removed, UV radiation at the surface would jump. That means DNA damage in organisms exposed to sunlight, more skin cancers, more mutations, collapse of food chains that depend on sensitive plankton, or plant life near the surface. Meanwhile, the atmospheric chemistry changes could also create nitrogen oxides, leading to acid rain and longer-term climate effects. There are real papers that try to quantify this. Some studies estimate that a gamma-ray burst within about a few thousand to maybe 10,000 light years could be enough to cause a mass extinction on Earth if it is pointed at us. There are even hypotheses that one of the extinction events in our own past, such as the late Ordovician extinction, might have been at least partly triggered by a burst like this. That is not proven, but it shows you that scientists take the possibility seriously enough to run the numbers. So, is our galaxy safe, or are we sitting in a shooting gallery? Gamma-ray bursts do not happen randomly everywhere at the same rate. Long bursts, which are the ones associated with collapsing massive stars like galaxies that are low in heavy elements and are forming stars very rapidly. Early in the universe, that kind of environment was common. Today, they are more often seen in smaller, irregular, metal-poor galaxies, not in big, mature spirals like the Milky Way. That is good news for you. The conditions here right now are not ideal for producing many long gamma-ray bursts. Short bursts from neutron star mergers are more connected to where old massive stars have lived and died, and can happen in a wider range of galaxies. But they tend to be less common and their beams may be narrower and less energetic at the very high end. Overall, when astronomers look at the rate of bursts per galaxy, they conclude that a single large galaxy like the Milky Way only sees a dangerous, close, well-aimed burst very infrequently. The odds that one happens in the next few million years and happens to be aimed perfectly at Earth are low. Low is not zero, though. Over billions of years, even rare events have a chance to hit something. The universe has time to roll the dice again and again. Think about all the planets in a galaxy sitting there for billions of years. Most of them will never be hit directly by a lethal burst. Some will. A promising biosphere might climb up to complex multicellular life and then get smashed back down, not by anything it did wrong, but by a star on the other side of the galaxy dying in exactly the wrong way. Now zoom out to a whole universe full of galaxies and planets. You're trying to explain why so far we do not see obvious signs of spacefaring civilizations out there. That is the Fermi paradox, the where is everybody problem. Gamma ray bursts give you one possible piece of the answer. They are natural random reset buttons. They do not care about your level of technology. If your planet happens to sit in the line of fire, your atmosphere gets hit, your surface life takes a massive blow, and evolution has to start again from whatever pockets survive. Repeat that over cosmic time, and you get a picture where complex, long-lasting technological civilizations are harder to sustain than simple habitability would suggest. Planets can be in the right zone around the right kind of star with liquid water and all the chemistry needed. But every so often a burst sterilizes them or knocks them back to bacteria and simple life. That kind of hidden hazard is exactly the sort of thing people mean when they talk about a great filter, a process that quietly removes most potential advanced civilizations before they can spread. So the universe has these invisible guns firing without warning across tens of thousands of light years, and you only survive because of distance geometry and luck. But you do not actually need an exotic cosmic explosion to threaten your biosphere. You live right next to a star that is perfectly capable of turning your planet into something unrecognizable, slowly, predictably, and without any outside help at all. You live on a timer that started ticking the day the sun lit up, and that timer is not set to infinite. It is set by what happens in the sun's core. The key point is simple: the sun is changing right now. It is not a constant lamp in the sky. In its core, hydrogen is fused into helium. As this goes on, helium builds up in the center. Helium does not fuse yet at today's core temperature, so it just sits there, making the core denser. A denser core contracts under its own gravity, and when it contracts, it heats up. A hotter core burns hydrogen in the surrounding layers faster, which makes the sun brighter. Stellar evolution models, checked against data from missions like Gaia that study lots of sun-like stars, tell you how big this effect is. Since the sun formed about 4.6 billion years ago, its luminosity has gone up by around 30 to maybe 50%. Today the trend continues. The sun's output is climbing by about 1% every 100 million years, roughly 10% every 1.1 billion years. On human timescales that looks flat, but on planetary climate timescales, that is deadly. So what does that do to Earth? As the sun brightens, the amount of energy hitting the top of our atmosphere, the solar flux, climbs. At first, the climate system and geology can compensate. Weathering of rocks, shifting continents, changes in carbon dioxide, all act like feedbacks that try to keep the temperature in a comfortable range. But that thermostat has limits. Once the sun is about 10 to 20% brighter than today, those feedbacks stop being enough. Climate models say that somewhere around about 800 million to 1 billion years from now, the extra flux tips Earth into what is called a moist greenhouse state. Surface temperatures rise, more water evaporates from the oceans, and the air becomes much more humid. Water vapor is itself a strong greenhouse gas, so the more you add, the more heat you trap, and the cycle feeds on itself. In a moist greenhouse, the upper atmosphere starts to get wetter. High in the atmosphere, water molecules are exposed to harsh ultraviolet light from the sun. UV photons break them apart into hydrogen and oxygen. Hydrogen is very light, so once it is free, it can escape to space. Slowly but steadily, your planet starts bleeding hydrogen and losing water for good. During this phase, complex life, anything like forests, animals, large ecosystems on land and in shallow oceans, takes a huge hit. Some studies suggest that complex multicellular life may be wiped out as early as 800 million years from now, long before the sun does anything dramatic like becoming a red giant. Microbes and extremophiles might hang on in sheltered environments, deep underground or high in the atmosphere, but the kind of biosphere you recognise, with rich ecosystems and large active animals, becomes impossible to sustain. Give it a bit more time, in the range of about 1 to 1.5 billion years from now, and the moist greenhouse process keeps marching. As more water reaches the upper atmosphere and more hydrogen escapes, the total amount of water in the oceans drops. Evaporation speeds up because temperatures keep rising, and the remaining water has a harder time cooling the planet. Eventually, most of the oceans are gone. What started as a blue world turns into a mostly dry planet with scattered seas or brine pools. Without oceans to buffer the climate, temperature swings get more extreme. At that point, even microbial life on the surface has a hard time. Life, if it still exists, is probably reduced to isolated niches, maybe in deep crustal rocks or under the surface. All of this happens while the Sun is still a fairly normal main sequence star, just somewhat brighter and hotter than today. The real big show is scheduled later. In about 5 billion years, the Sun will have used up most of the hydrogen in its core. When that fuel is gone, the balance that has kept the Sun stable for billions of years breaks. The core, now mostly helium, contracts and heats further, and hydrogen burning moves into a shell around it. The outer layers respond by expanding and cooling. The Sun swells into a red giant. In the red giant phase, the Sun's radius can grow large enough to swallow the orbits of Mercury and Venus. Whether Earth's orbit is engulfed or not is still an open question, because the Sun will also lose mass through a strong stellar wind, which lets Earth drift outward. Some models say Earth gets dragged into the Sun's bloated envelope and vaporized. Others say it just barely escapes, but that escape is not good news. Even if Earth stays outside the physical surface, it will be so close to a hugely brighter red giant that its surface is heated to thousands of degrees. The crust melts, the planet becomes a glowing ball of magma. Any trace of water, atmosphere, or past life is gone. After that, the Sun will blow off its outer layers as a planetary nebula, leaving behind a white dwarf, a dense, hot core about the size of Earth but roughly half the mass of the Sun. Earth, if it still exists at all, will just be a dead rock or slag orbiting a fading ember. Here is the blunt truth. Earth was never meant to be permanent. It is not a fixed, eternal home. It is a temporary environment with a habitable window you can roughly calculate with real numbers. From the formation of the Sun until now, conditions have been good enough for liquid water and complex life for only a slice of time, maybe a few billion years wide. In another billion years or so, that window will close because the Sun simply does what stars do. So when you think about the future of humanity, or any civilization on this planet, you are talking about something that is riding on top of a slow, predictable disaster. The slow burn of the Sun does not care about technology or culture. It is baked into nuclear physics and gravity. If intelligent life wants to survive longer than that, it has to leave, or radically re-engineer its star or its orbit, or both. And even if you imagine solving that problem, building starships or moving worlds, there is another layer of danger waiting. The solar system itself is not a fixed, isolated bubble. It is moving through a galaxy full of other stars and massive objects, any of which can, over long enough times, nudge planets out of their orbits and turn a stable system into a chaotic one. Your solar system is not nailed down. It's more like a crowded dance floor where partners occasionally get flung into the dark. Start with the big picture. The Sun is not sitting still in space. It orbits the centre of the Milky Way, and so do hundreds of billions of other stars. All of those stars are moving on slightly different paths, at different speeds, in a gravitational field that is not perfectly smooth. Over millions and billions of years, some of them pass relatively close to each other. Not crash into each other close, but close enough that their gravity reaches out and tugs on anything loosely bound. Around our own Sun, far beyond the planets, there is a huge cloud of icy bodies, the Oort cloud, stretching maybe out to tens of thousands of times the Earth-Sun distance. Those objects are only weakly held by the Sun's gravity. When another star passes within a light year or so, its pull can disturb that cloud. That means comets get nudged. Some are kicked inward into the inner solar system. Others are thrown out entirely. Each close pass is like shaking the edge of the system, and the effects can show up tens of millions of years later as bursts of comets falling toward the Sun and sweeping through planetary orbits. This is not just a theoretical game. With modern data, especially from the Gaia mission, astronomers can track the motions of millions of stars with high precision. When they run those orbits backward and forward in time, they find real examples of close encounters. One well-known case is a star called Schultz's star, which appears to have passed within about a light year of the Sun around 70,000 years ago, almost certainly going right through the outer Oort cloud. Others have been identified that will pass relatively close in the future, not dangerously close to Earth, but close enough to tug at distant comets. The same kind of analysis also reveals stars on paths that bring them very close to other stars' systems, so this galactic pinball is not abstract, it is happening. Now zoom in on planets. When a star flies by, its gravity doesn't just act on the comets. If it gets close enough, it can slightly change the orbits of the planets too. For a single distant pass, the effect on a planet like Earth is tiny, basically nothing you could measure in a lifetime, but gravity is patient. Over billions of years, many small nudges from passing stars, from giant molecular clouds, from the combined pull of other planets can add up, and we have direct evidence that planetary systems do not always stay tidy. We have found hot Jupiters, gas giants skimming right next to their stars, which almost certainly formed farther out and then migrated inward, disrupting whatever was in their way. We see planets on very elongated, tilted orbits. We see systems where the planets are packed so tightly that they are right on the edge of stability. All of that tells you that planet orbits move over time. Take it one step further. What happens when the nudges are big enough or the system is chaotic enough that a planet is no longer held securely at all? Then you get a rogue planet. Surveys using a technique called microlensing, where a planet's gravity briefly magnifies the light of a background star as it passes in front, suggests that these free-floating worlds are common. Some estimates say there might be as many rogue planets in the galaxy as there are stars, maybe more, meaning there could be trillions of planets that have been kicked out of their original systems and now drift through interstellar space with no sun. These worlds are dark, cold on the surface, only warmed by leftover internal heat or maybe a thick insulating atmosphere. They are almost impossible to see directly, but their existence tells you something. Ejection is a real outcome. Planetary systems are not perfectly safe cradles. In a long enough timeline, some planets get thrown away. So what about Earth? Is there a real chance it ends up flung into the dark or pulled into the sun or smashed out of its orbit? When scientists run detailed N-body simulations of the solar system, where they track the gravitational interaction of all the planets over billions of years, they discover something important. The system is chaotic on very long timescales. Chaos here doesn't mean random. It means that tiny changes in the starting conditions grow over time. Two simulations that start almost the same can end up with very different details after billions of years. The good news is that for the next few hundred million, even a few billion years, those simulations agree on one basic point. The inner planets, including Earth, stay in roughly their current orbits. The chance of a catastrophic orbital change in the near term is essentially zero. The solar system is very stable on the timescale that matters to human civilization, and even on the timescale where the sun's brightening becomes the main problem. But if you extend those simulations out further and further, eventually you start to see rare but serious events. In some runs, Mercury's orbit gets more eccentric and crosses the path of Venus. In others, interactions between Jupiter and Saturn slowly pump up orbital eccentricities until one of the inner planets either hits another or falls into the Sun. Add in the possibility of a really close stellar encounter on top of that, and the long-term risk of major orbital rearrangement grows. Over tens of billions of years, the probability that the solar system's orbits are completely reshuffled, or that one or more planets are ejected or destroyed, becomes significant. In practice, the Sun will leave the main sequence and go red giant long before most of that extreme long-term chaos plays out, so the star kills the habitability of Earth first. But the key idea stands: there is no guaranteed forever orbit. Gravity keeps everything moving, and those motions are sensitive to small changes. Over long enough times, no planetary system is truly safe. Psychologically, this hits something deep, because we like to picture the solar system as a clean clockwork machine. Nice circular orbits, smooth motion, everything repeating in a perfect pattern forever. The reality is more like a slow-motion bar brawl, with massive bodies constantly tugging on each other, trajectories shifting little by little, and occasionally something getting thrown out of the room. Now combine that with everything you've already heard: the star that will eventually overheat your world, the passing stars and rogue planets telling you that orbits are not sacred, the gamma-ray bursts that can wipe a planet's biosphere from across the galaxy, the black holes that can swallow anything that gets too close. When you put all of that together, you get a universe that is not calmly waiting for life to spread. It is a universe that constantly tests planets and biospheres with slow and fast disasters. So when you look up at the sky and ask, where is everybody? Why don't we see clear signs of other advanced civilizations? One uncomfortable answer is this: maybe most of them never make it very far. Maybe there is a great filter, a set of brutal steps and hazards that most worlds never survive, and the silence you hear is not an accident. It is a warning. The silence in the sky might be the loudest warning sign you'll ever hear. Look at what we know right now. The Milky Way alone has something like 100 to 400 billion stars, and at least that many planets, probably more. Across the whole universe, there are trillions of galaxies like that. On top of that, we've now confirmed over 6,000 exoplanets, with thousands more candidates, and a good chunk of them sit in their stars' habitable zones, where liquid water could exist. With those numbers, you'd expect the night sky to be full of obvious signs of someone: giant engineering projects, powerful radio beacons, weird infrared signatures from stars wrapped in megastructures. What we actually see is nothing that looks clearly artificial. No probes buzzing around our solar system, no giant light patterns in other galaxies, no unambiguous techno-signatures. The sky is busy with natural stuff, but silent in a technological sense. That mismatch between we should see something and we see nothing is the heart of Fermi's question: where is everybody? Now add another layer: timing. The galaxy is old. The Sun is about 4.6 billion years old, but stars like the Sun have been forming in the Milky Way for a long time before that. Studies of the so-called galactic habitable zone, the region of the galaxy where conditions are good for Earth-like planets and long-term stable orbits, suggest that many Sun-like stars with potentially habitable planets formed billions of years before the Sun did. One influential analysis found that most stars in that zone formed between about 8 and 4 billion years ago, and that roughly 75% of them are older than the Sun. If that's right, then a typical habitable system in our galaxy might be a couple of billion years older than ours. That is a huge head start. On Earth, it took about 4 billion years to go from simple life to a technological species. So if evolution is even vaguely similar elsewhere, a lot of other planets had enough time to produce intelligent life long before we showed up. Some of them, in theory, could be millions or hundreds of millions of years ahead of us. So again, why don't we see anything that looks like a million-year-old civilization? The Great Filter is one possible answer. The idea is simple and brutal. Start with a galaxy full of stars and planets. Think about the chain of steps you need to go from a bare rock to a civilization that can spread through space and leave obvious traces. You need a right kind of star, a stable planetary system, chemistry that produces self-replicating molecules, then single-cell life, then complex cells, then multicellular organisms, then intelligence, then technology, then a civilization that doesn't immediately wipe itself out and actually expands. The Great Filter says, somewhere in that chain, there are one or more steps that are insanely unlikely. The universe tries them again and again and almost always fails. From our point of view, that creates two main possibilities. The filter is mostly behind us or mostly ahead of us. If the filter is behind us, it means the really hard parts with things like life starting at all, or the jump from simple cells to complex cells, or the jump to multicellular life. Maybe that took such freak coincidences that almost no planets ever get that far. In that scenario, we are rare and early, maybe effectively alone as a technological species in the galaxy, because almost nobody else makes it to our level. That sounds flattering, but it also means there are no older civilizations to learn from, no proven path to long-term survival. If the filter is ahead of us, the story gets darker. That would mean it is relatively easy to get to where we are now, but incredibly hard to get past this stage and become a stable, long-lived, spacefaring civilization. In that case, the reason the sky is quiet is that most civilizations reach a certain level of technology, and then, one way or another, they hit a wall and disappear. So what could that wall be? Some candidates are cosmic, some are self-inflicted. On the cosmic side, you've already seen some of them. Gamma-ray bursts that can strip atmospheres and trigger mass extinctions from thousands of light years away. Stars that slowly brighten and cook their planets. Planetary systems that go unstable over time and throw worlds into deep space. Supervolcanoes that reset climates. Asteroid impacts that erase whole branches of the tree of life. Earth has had at least 5 major mass extinction events in the last 500 million years, wiping out most species each time and forcing life to start over from whatever survived. The cosmos does not promise a smooth ride. On the self-inflicted side, the list is long and uncomfortable because it includes things we're already playing with. Nuclear weapons that can destroy global infrastructure in hours. Uncontrolled artificial intelligence that might act in ways we cannot predict or stop. Runaway climate change, where we push the planet into a new stable state that cannot support our current civilization, with modern projections showing degrees of warming this century that would restructure coastlines, agriculture, and weather patterns worldwide if we keep emitting. Resource collapse, global wars, anything that can drag a technological society back down or wipe it out completely. The key point is not that any one of these is guaranteed to happen. The key point is that you only need 1 or 2 of them to be common outcomes for the average civilization, and suddenly the galaxy looks the way it does now, full of planets, full of life chances, but quiet in the radio, dark in megastructures, empty of visible empires. Most species make it partway up the ladder, and then get knocked off by something, external or self-inflicted, before they ever become loud on cosmic scales. There is a nasty twist in the logic of the Great Filter. If we look out and start finding lots of simple life, bacteria-level stuff on other worlds in our own solar system or nearby systems, that is exciting, but it also suggests that the early steps are not that rare. The more common life looks on the simple levels, the more likely it is that the real filter is higher up, at stages we have not passed yet, like forming a stable global civilization that survives its own technology. On the other hand, if we search and never find any life at all, not even microbes, that is lonely, but it would mean we may be already past the hardest hurdle and might have a better shot long term. You're stuck between 2 scary options. Either we are freakishly early and alone, sitting in a galaxy where almost nobody else ever got out of the mud, or we are perfectly normal on the same track almost everyone else followed straight into oblivion. Alone is terrifying because it means no help is coming, no backup, no second chance if we mess up. Normal is terrifying because it hints that the default outcome for civilizations at our level is failure. And remember, this whole discussion is happening in a universe where we don't even fully understand what most of the matter is. All the stars, planets, gas, dust, everything you can see is just a small fraction of what's actually there. The rest is an invisible component that shapes galaxy formation, bends light, and passes right through you all the time, and we still don't know what it is made of. 85% of the matter in the universe goes straight through you, through the planet, through everything, and we still don't know what it is. Start with the evidence. Take a spiral galaxy and measure how fast the stars orbit as you move outward from the center. If only the visible stars and gas were there, gravity should get weaker with distance and the outer stars should orbit more slowly, like planets in the solar system. But when astronomers actually measure those rotation curves, the speeds stay flat, or even rise slightly, far out into the dim outer regions. That only makes sense if there is extra mass spread out in a big, invisible halo around the galaxy. Then look at galaxy clusters. When you add up all the visible mass from stars and hot gas, it isn't enough to keep the galaxies bound at the speeds we observe. Gravitational lensing makes the case even stronger. Clusters bend and distort the light from background galaxies into arcs and multiple images. The amount of bending tells you how much mass is there, and again, it comes out far higher than what you see in normal matter. Finally, look at the universe on the largest scales. The cosmic microwave background, the afterglow of the Big Bang, has tiny temperature fluctuations. The pattern of those fluctuations, the power spectrum, depends on how much ordinary matter, dark matter and dark energy there is. When you fit the data, you get a consistent picture. Normal matter is only about 5% of the total energy content. Dark matter is about 5 times that, around 25%. The rest is dark energy. That same combination also explains how structures grow from tiny early ripples into galaxies and clusters over billions of years. So dark matter is not a wild extra add-on. It is the simple way to make all these independent observations line up. Something with gravity that does not emit or absorb light the way normal matter does is there. So what could it be? Physicists have built a bunch of serious candidates, not sci-fi, but actual models inside or just beyond the standard model of particle physics. One big class is WIMPs, weakly interacting massive particles. These would be heavy particles that feel gravity, and maybe the weak nuclear force, but not electromagnetism. In the early universe, they would have been produced in large numbers, and then froze out with the right relic density to match today's dark matter. For years, WIMPs were the favourite, partly because they would naturally pop out of some supersymmetry models. Another possibility is actions, very light particles originally proposed to solve a different problem in quantum chromodynamics, the strong CP problem. Under the right conditions, a huge number of axions produced in the early universe could behave like a cold dark matter fluid, filling halos and driving structure formation. There are also sterile neutrinos, hypothetical neutrinos that do not feel the weak force either, only gravity. If they exist with the right masses, they could act as warm dark matter, affecting small-scale structure in specific ways. And then there are models where dark matter particles can even interact with each other through some new force, self-interacting dark matter, which might help explain some detailed features of galaxy cores. So you have a whole menu of candidates with different masses and interaction strengths. You might think, with so many options, surely we would have found something by now, but that brings you to the most unsettling part. To actually catch dark matter, you build detectors deep underground, inside mountains or mines, to shield them from cosmic rays. Experiments like Xenon NT, LZ, Panda X and others use large tanks of ultra-pure liquid xenon or similar materials. The idea is simple: wait for a dark matter particle to occasionally bump into a nucleus in the detector, producing a tiny flash of light and a bit of charge that you can record. If WIMPs exist in a certain mass and interaction range, these detectors should see a small but steady stream of such events. So far, the result is nothing convincing. Experiment after experiment has come back with null results, ruling out more and more of the parameter space where WIMPs could hide. The simplest versions of WIMP models are under serious pressure. Axion searches with resonant cavities and other tricks also keep tightening the net without a clear detection. Every time an experiment fails to see anything, the story gets weirder, because the gravitational evidence for dark matter is still there, but the easy particle explanations are being squeezed. Meanwhile, in computer simulations, dark matter is absolutely central. When you run n-body simulations of the universe's growth, you start with a nearly smooth distribution, add tiny fluctuations, and then let gravity do its thing. The dark matter collapses first, forming a web of filaments and clumps, the cosmic web. Gas falls into those dark matter potential wells, cools, forms stars, and builds galaxies. When you look at the results, They reproduce the large-scale pattern of galaxy clustering we actually see in surveys, long filaments, sheets, and voids. In that picture, galaxies like the Milky Way are really just bright tracers sitting in the centres of massive invisible halos. The shape of your galaxy, the way it orbits in the cluster, even the history of mergers that built it, are all dominated by dark matter. The stage on which your entire cosmic history plays out is sculpted by something you have never seen directly, and it gets more personal. If dark matter is made of some kind of particle, there is a dark matter halo around the Milky Way, and the solar system is moving through it. That means right now, dark matter is passing through your body, through the walls, through the whole Earth, all the time. It does not hit your atoms in any noticeable way, because its interaction with normal matter is so weak. On human scales, it is as if it is not there. On galactic scales, it is the main thing setting the rules. So you are living in an invisible ocean. Ordinary matter, everything you know is the foam on top. The large-scale architecture of the universe, where galaxies form, how clusters grow, how the cosmic web looks, is dictated by a sector of reality we barely understand, that we have never touched in the lab. And dark matter is not the only place where our best theories gonna start to mess with your sense of what is real. If you take the same ideas about entropy and fluctuations that explain everyday physics, and you push them into the extreme far future, you get a scenario where it might be more likely for a random, isolated brain with fake memories to pop out of chaos than for a whole low-entropy universe like this one to exist. Physics says it might be more likely that you're a random brain floating in chaos than a person living on a real planet, and if that doesn't bother you yet, it should. Start with entropy again. In a low-entropy state, things are ordered, structured, special. In a high-entropy state, things are messy, random, spread out. The second law says that in an isolated system, entropy tends to increase. If the universe lasts forever and drifts towards some high-entropy equilibrium, you might think the story ends there, cold and smooth. But high entropy doesn't mean absolutely nothing ever happens. Even in a high-entropy state, you still have fluctuations, random blips where, just by chance, a small region becomes a bit more ordered than average. Now push that idea until it gets uncomfortable. If the universe exists for an absurdly long time, and if it's big enough or eternal enough, then extremely unlikely fluctuations are still guaranteed to occur eventually. Most of the time, you just get tiny things, a bit of density variation here, a little cluster there. But in principle, given enough time, a fluctuation could assemble something wildly specific, like a functioning brain, with a pattern of connections that encode memories, preferences, fears, everything. Nothing mystical, just atoms and molecules bumping around until by chance they line up as you, complete with a full set of fake memories of a life you never actually lived. That's what people mean by a Boltzmann brain. A conscious brain that pops out of chaos as a random fluctuation, exists briefly, has experiences, then dissolves back into noise. From the inside, it feels exactly like being a normal person. From the outside, it's a meaningless statistical accident. This is Boltzmann's nightmare. Ludwig Boltzmann originally used the idea of fluctuations to explain how structures could briefly appear in a mostly high-entropy universe. Later thinkers took that all the way. If you compare probabilities, which is more likely, the entire observable universe starting in an extremely low-entropy state like the Big Bang, with smooth radiation and matter spread almost perfectly evenly, or a single brain-sized chunk of matter randomly arranging itself into a functioning mind with detailed memories of such a universe. Creating a whole low-entropy universe is an enormous drop in entropy, incredibly unlikely as a fluctuation. Creating one brain is still ridiculously unlikely, but it's a much smaller entropy change. So, in a naive, eternal, high-entropy universe, it looks like brains should vastly outnumber full universes with people. That means a typical conscious observer in that universe is not a person living on a stable planet billions of years after a Big Bang. A typical observer is a Boltzmann brain floating in the chaos, with fake memories. Now turn that back on yourself. If some cosmological model says the overwhelming majority of observers are a random one-off brains with false histories, and only a tiny fraction are ordinary beings like you think you are, then under that model, you should rationally expect to be one of the random brains, because that's what's most common. But that prediction clashes with your whole experience. You see a consistent, stable external world. You can do experiments, you can build theories that keep working. If you were a Boltzmann brain with fake memories, none of that evidence would actually be evidence. It would just be part of the fake memory pattern. That is the modern Boltzmann brain problem. Cosmologists realize that some naive eternal cosmology ideas, especially ones where the universe asymptotically settles into a de Sitter state and just hangs around forever with small thermal fluctuations, predict that Boltzmann brains should vastly outnumber normal observers. If your theory says almost everyone is a Boltzmann brain, but you feel like a normal observer in a normal galaxy, then your own existence as a non-insane observer is evidence against the theory. It makes your current experience wildly atypical, and that's a red flag. Serious people treat this as a real constraint. Physicists like Sean Carroll and others have argued that any cosmological model that predicts you are probably a Boltzmann brain is self-defeating. If the theory says your observations are almost certainly fake, then you cannot use those observations to justify the theory. That makes the whole framework logically unstable. The conclusion is harsh but clear if you build a model of the universe and it spits out Boltzmann brains dominate. You have to throw that model out, even if it looked elegant or simple in other ways. So this weird thought experiment does real work. It filters cosmologies. It tells you that acceptable models must have some mechanism that prevents Boltzmann brains from dominating. Maybe the universe doesn't last long enough in a quiet, high-entropy state. Maybe its vacuum decays. Maybe expansion changes. Maybe something about quantum gravity cuts off the phase where those brains would form in huge numbers. Whatever the fix is, it has to bring the count of ordinary observers like you above the count of random flickering brains. But there's a deeper horror in this, and it hits directly at how you relate to reality. You're used to thinking that evidence comes from experience, from measurements, from the apparent stability and coherence of the world around you. The Boltzmann brain scenario shows you a logically consistent universe where all of that exists only inside a momentary mind, with no external world behind it. And yet inside that mind, the experiences feel exactly like what you're having now. So when physics tells you that some possible universes make it more likely for you to be a fake brain with fake memories, it's really asking a brutal question. What does evidence even mean if there are logically possible setups where every piece of evidence you ever see is part of a hallucination generated by random chance? The way out is to demand theories that do not put you in that position. Theories where being an ordinary observer in a vast real cosmos is the normal outcome, not an extreme exception. But notice what that means. Constraints like no Boltzmann brain domination, and no vacuum that lives forever in quiet equilibrium, are not aesthetic choices, they are survival rules for our theories. When you apply them, you discover something even more unnerving. Our best current ideas about empty space itself make a prediction that is off by about 120 orders of magnitude. According to those calculations, the default universe should either explode apart instantly or be crushed long before galaxies can form. And yet here you are. According to quantum field theory, empty space should be so energetic the universe would rip itself apart instantly. Instead, you're sitting here, calmly watching a video. In quantum field theory, you don't just have particles, you have fields filling all of space for every kind of particle. Even when there are no particles around, those fields still have activity. They fluctuate, they have a minimum energy built in called zero-point energy. That means even the vacuum, the state with no real particles, carries energy. Now take that seriously and do the naive thing. You add up the zero-point energy from all the known quantum fields, up to some high energy cutoff where you think your theory stops being valid, maybe near the Planck scale. When you do that, you get an absolutely enormous number for the vacuum energy density, the energy per unit volume of empty space. That energy density would act like a cosmological constant in Einstein's equations, pushing on space-time. Here is the problem. When we actually measure how fast the universe is expanding using supernovae, the cosmic microwave background, galaxy clustering, all of that, we infer real, physical dark energy density, and it is tiny. It is not zero, but it is very small. If you express the naive quantum field theory estimate and the observed value in the same units, the theory overshoots by around a factor of 10 to the power of 120. That is often called the worst theoretical prediction in physics. To get a feel for that, 10 to the power of 120 is a 1 with 120 zeros. Comparing the naive vacuum energy to the real one is like predicting the mass of the Earth and getting something bigger than the mass of the observable universe. It is not a small mismatch, it is a total disaster. So you could try to be clever, you say. Fine, maybe there is a bare cosmological constant term in Einstein's equations with one sign, and the quantum zero-point contributions from fields add up with the opposite sign, and they almost cancel. That way, the huge pieces subtract off and the leftover, the net value, is small and matches what we observe. But almost cancel here means something extreme. Those big contributions have to line up and cancel each other to about 1 part in 10 to the power of 120 and still leave behind a tiny residue that is not exactly zero. Just small enough to let galaxies form, but big enough to accelerate the universe today. It is like balancing the books of the entire universe to 120 decimal places, and at the end of that, you still have a few cents left over that quietly control the fate of cosmic expansion. This is the fine-tuning from hell. Our equations do not tell us why the cancellation is that precise. They just let us dial in a parameter so the math fits the data. It works, but it feels like cheating. You're left with this sense that the universe's vacuum energy is ridiculously special, with no good reason given. To get out of that, some people bring in bigger frameworks. In string theory, for example, the equations naturally allow an enormous number of different possible vacuum states, each one with its own value of the vacuum energy, its own effective cosmological constant. That picture is sometimes called a landscape with a huge menu of possible universes. Then you add another idea, a multiverse. Maybe different regions of a larger space-time settle into different vacuum states. Each region, each pocket universe, expands with its own cosmological constant. Most of them have vacuum energies that are way too large, either positive or negative, and those regions either expand so violently that matter never clumps into galaxies, or collapse back in on themselves quickly. Only a tiny subset, the ones with very small vacuum energy, manage to form galaxies, stars and planets. In that context, the answer to why is the cosmological constant so small becomes anthropic. Because if it were not small, you would not be here to ask the question. Out of countless possible vacuum energies, you inevitably find yourself in a rare patch where the value happens to be in the narrow window that allows chemistry and observers. You do not need a dynamical mechanism to set it. Selection effects in a multiverse do the job. That is the band-aid. But notice what you just did. You traded one kind of discomfort for another. Instead of a single universe with a mysterious, finely tuned parameter, you now have a vast ensemble of universes, most of which are sterile and short-lived, and you live in one of the vanishingly rare ones that can host observers. You have not really explained the value, you have just said, we see this value because any other value would not let us exist. Why is this terrifying? Because when you combine our two best frameworks, quantum field theory and general relativity, and you ask a very basic question, what is the energy of empty space? They scream the wrong answer at you. They say, by default, vacuum energy should be enormous. Universes should either blow apart so fast that nothing binds, or curl up and die before any complex structure forms. The universe you actually live in, where the vacuum energy is small, positive, and only starts accelerating expansion after billions of years, is not the generic outcome. It is a special case sitting in a ridiculously tiny part of parameter space. Your existence is telling you that something deep in our understanding of space-time and quantum fields is missing. Either there is a hidden mechanism that sets the vacuum energy almost, but not exactly to zero, or there is some extra principle, some new kind of selection rule that forbids all the naive possibilities that seemed allowed on paper. Like now, we do not know which is true. We just patch the equations to fit the data and move on, fully aware that we are building on a number that makes no sense. And here's the part that links back to the rest of this nightmare list. If vacuum energy is this strange and this sensitive, if the ground state of the universe is something that can be shifted by deep physics we do not yet understand, then you cannot be sure that the current value is final. If the universe has already gone through multiple transitions where its sort of fields and vacuum energy changed, there is no guarantee we are living in the last version. Another phase change in the future, even a tiny one in the wrong direction, would rewrite the rules of the game again, maybe in a way that life cannot survive. So the next question practically asks itself, if the universe has already changed its own setting several times since the Big Bang, why assume it is done updating now? What if there is another phase transition coming, one more cosmic patch that does not have to be gentle and does not have to leave anything like us behind? The universe might not be done changing its rules, and the next phase transition doesn't have to be gentle. Look back at cosmic history. Right after the Big Bang, the universe was incredibly hot and dense, and the laws of physics did not look like they do now. As it expanded and cooled, it went through a series of phase changes, just like water going from steam to liquid to ice, except here the things freezing out were fundamental forces and particles. There was a time when the electromagnetic force and the weak nuclear force were merged into a single electroweak force. As the universe cooled past a critical temperature, that symmetry broke. The electroweak force split into the electromagnetic and weak forces we know today, and particles like the W and Z bosons and the Higgs field picked up their roles and masses. Go further back and quarks were not locked into protons and neutrons, they were in a quark-gluon plasma. When the universe cooled again, quarks got confined into hadrons. Each of these transitions changed what could exist, what was stable, how matter clumped, how stars and atoms would eventually form. So the universe has already done multiple rule changes on its way from the Big Bang to now. None of those required anyone to push a button. They were built-in consequences of cooling and of the shape of the underlying field potentials. That should already disturb you because it means the laws you experience are not absolute. They are the result of which phase the universe currently happens to be in. Now connect that to dark energy. In many models, dark energy is not just a fixed number. It comes from some dynamical field spread through space. That field sits in a particular configuration, a local minimum of its potential, like a ball resting in a valley that is not necessarily the lowest point in the whole landscape. That picture is very similar to what you heard in the vacuum decay story with the Higgs field. The current dark energy value would then be the energy of that state. If the field is only in a local minimum, not the true global minimum, then quantum mechanics always leaves a door open. There is a tiny chance that somewhere the field tunnels through the barrier into a lower valley. That event would create a bubble where the dark energy density is different, maybe much lower, maybe negative. Once formed, that bubble is more stable than the old phase, so it expands again at close to the speed of light. Inside the bubble, the effective cosmological constant has changed, and it does not have to stop at just changing the dark energy. A new phase could rearrange multiple fields at once. Fundamental constants could shift, particle masses could change, the relative strengths of forces could be different. In extreme scenarios, even the effective dimensionality of space-time could alter, though that is more speculative. From our perspective, the crucial fact is simple. The rules that allow atoms, chemistry, stars, and life are tied to the current phase. A new phase might not support any of that. So what would a new phase transition actually do to a universe like ours? Outside the bubble, everything looks normal, galaxies evolve, stars live and die, life goes on. Inside, the entire structure of matter could be unstable. Protons might decay rapidly, atomic bonds might not hold, or there might be no stable nuclei at all. The vacuum energy might be negative enough to force rapid recollapse. From the outside, there is no warning because the bubble wall is racing at almost light speed. From the inside, there are no observers to describe it. It is another version of the vacuum decay nightmare, but now driven by whatever field is responsible for dark energy, not necessarily the Higgs. This is not just a fantasy glued on top of the data. When cosmologists fit observations, they usually write dark energy in terms of that parameter W, the ratio of pressure to energy density. For a pure cosmological constant, W is exactly -1 and never changes. But the actual measurements still come with error bars. Current data say W is very close to -1, but they do not nail it exactly and they leave room for W to change over time. There are hints, depending on which data sets and analyses you trust, that dark energy might be evolving slightly, either getting weaker or stronger as the universe ages. That kind of behaviour is exactly what you expect if dark energy comes from a field rolling slowly in some potential, maybe heading toward another phase. Combine that with the earlier uncertainty about the universe's long-term fate, big freeze, big rip, big crunch. All those different endings boil down to details of how dark energy behaves in the future. If it stays constant, you freeze. If it ramps up, you rip. If it weakens or turns negative, you crunch. If it jumps discontinuously in a phase transition, you get something even more abrupt, a sudden change of vacuum that drags the entire cosmic evolution onto a completely different track. The same knobs that set the expansion history are the ones that could, in principle, flip you into a new phase. So you are living in a universe that already has a track record of changing its own laws as it cools, and you are currently measuring a component of it, dark energy, that looks almost constant but not perfectly nailed down. That is exactly the situation where phase transition models live, a field that seems frozen now but might not be in the ultimate ground state. Here is the punchline. The universe has already gone through multiple patch updates in its fundamental laws, and there is no deep principle that says it has to stop with the version you happen to find comfortable. For all we know, we are in the middle of the changelog, not at the end. If there is a lower energy phase waiting, if some field is only metastable, then at some random time in the far future, or in the next moment, a bubble could form somewhere and start rewriting everything. On the timescales that matter to you, this is not a practical risk. The calculated tunneling probabilities in reasonable models make these events insanely rare on human or even stellar lifetimes. But as with vacuum decay, the real horror is not this will happen tomorrow. It is, this is allowed by the same physics we trust for everything else, and we do not know why it has not already happened, or whether it is even avoidable. And while the universe plays with these enormous phase changes on cosmic scales, we are busy on a tiny planet, building machines that recreate early universe conditions in miniature, smashing particles together at higher and higher energies, and writing safety reports where physicists have to prove their experiments probably will not trigger a catastrophic transition in the matter around us. What if there's a form of matter that eats normal matter? And we've already been looking for it on purpose. In our current picture, protons and neutrons are made of up and down quarks bound together by the strong force. Quantum chromodynamics, the theory of that force, allows more exotic combinations. In some models, there could be a more stable phase of nuclear matter made of up, down, and strange quarks mixed in roughly equal amounts. That hypothetical stuff is called strange quark matter. If it really is more stable than ordinary nuclear matter, then a small lump of it, a strangelet, could in principle exist as a tiny ultra-dense droplet. On its own, that's already weird, but the real nightmare comes from one extra step. In some speculative scenarios, if you had a negatively charged strangelet and you dropped it into ordinary matter, it wouldn't just sit there, it could act like a seed. When normal nuclei touched it, the quarks inside those nuclei could rearrange into the more stable strange configuration, releasing energy and adding to the strangelet. That bigger strangelet could then convert more surrounding matter, and so on. In the extreme version, you get a runaway process. where a chunk of normal matter is eaten and turned into strange matter. Scale that up and you see the horror story. A strangelet produced in a collider or arriving from space touches ordinary matter, catalyzes conversion, and the chain reaction keeps going until the entire planet is turned into a dense, hot ball of strange matter, like a miniature strange star. No explosion you can outrun, no slow climate shift, just a phase change ripping through the planet at nuclear speeds. This is very speculative, but it was taken seriously enough that when big colliders like RHIC in the US and the LHC at CERN in Europe were planned, safety panels were set up to check these scenarios in detail. They didn't just wave it off. They wrote formal reports asking, could our heavy ion collisions make strangelets? If they did, could those strangelets be stable? If they were stable, could they be dangerous? The main argument against danger is simple and powerful. Nature has already been running a much larger, much higher energy experiment for billions of years. Ultra-high energy cosmic rays slam into Earth's atmosphere constantly, with energies far beyond what our colliders can reach. They also hit the surfaces of white dwarfs and neutron stars, places with incredibly dense nuclear matter. If it were easy to make dangerous strangelets in high-energy collisions, and if those strangelets could reliably start runaway conversion, you would expect at least some of those stars, or planets like ours, to have been converted already. But neutron stars exist, and they look like neutron stars, not strange stars. Their masses and radii match what you expect for normal neutron matter in most cases. If strangelets that eat nuclear matter were easy to make and long-lived, neutron stars would be the perfect targets, and they would not look the way we see them now. The continued existence of ordinary neutron stars over billions of years of cosmic ray bombardment puts very strong constraints on any dangerous strange matter scenario. The same logic applies to hypothetical mini black holes. People worried, what if high-energy collisions make tiny black holes that then grow? Safety studies pointed out that if such black holes could be created at all by these energies, cosmic rays would have been making them in the atmospheres of neutron stars and white dwarfs for ages. Those stars are still there. So if mini black holes are possible, they must either evaporate almost instantly or interact in a way that does not destroy their hosts. In the end, the safety reports for RHIC and the LHC concluded that there is no credible risk. The energies are too low compared to the cosmic ray experiments nature already runs, and astrophysical observations rule out the simple disaster scenarios. That's why those machines were allowed to turn on and run, and they have for years, without any sign of exotic matter eating the world. But there is a psychological angle here that you cannot just shrug off. Physicists had to sit down and seriously ask, is there any way our experiment could accidentally trigger a planet-scale phase transition? They had to calculate, compare, and then write official documents explaining why their experiments probably would not destroy the Earth. They had to lean on the behavior of neutron stars, white dwarfs, and billions of years of cosmic rays as part of the safety case. That tells you something about where we are as a species. We are now building machines that push matter into regimes that only existed naturally in the early universe or in the cores of dead stars. We do it carefully, we check the risks, we rely on physics that has been tested in many ways, but we are still forced to think about the idea that there might be unknown phases of matter that are more stable than the one we live in, and that touching them could be catastrophic. So even though the best evidence says strangelet doom is not going to happen, the concept itself sits in the background with all the other stories you've heard. Vacuum decay, phase transitions, cosmic doomsdays. It's another reminder that what feels normal to you, ordinary atoms and nuclei, might not be the deepest, most stable way for matter to exist. And that brings us back to something even bigger and more unsettling. All this time you've been assuming that if dangerous things exist in the universe, they're at least indifferent. Gamma ray bursts don't aim, black holes don't hunt, phase transitions don't target anyone, but what if there are others out there who are not indifferent? Who can aim? Who can choose? What if the universe is quiet, not because it's empty or safe, but because everyone who has survived long enough has learned that the only winning move is to shut up and hide? What if the universe is quiet, not because it's empty, but because everyone is hiding from everyone else. You already saw the great filter idea, something out there or in here, that wipes out most attempts at advanced life. The dark forest picture is a different twist on the same basic problem. It starts with the Fermi paradox and adds cold game theory. There are hundreds of billions of stars in the Milky Way. We now know of thousands of exoplanets, and a good fraction sit in habitable zones. We have no reason to think the chemistry that built life here is unique. So any civilization with basic astronomy will quickly realize two things. First, other civilizations could exist. Second, you have no idea what their intentions are. Now add some basic constraints. The speed of light is a hard limit. Communication between stars takes years to millennia. You do not get quick conversations, you get very slow exchanges. Meanwhile, technology can change quickly. A civilization that looks harmless today could be able to build planet-killing weapons or relativistic projectiles in a few centuries. By the time you see a signal, analyze it, decide how you feel about it, and send a reply, the sender could be far more advanced or completely gone. This is where game theory kicks in. Imagine you are one civilization in a galaxy full of possible others. You don't know how many there are, you don't know where they are, you don't know their values or risk tolerance. You do know that you are vulnerable. A sufficiently advanced civilization could, in principle, launch a preemptive strike from a long way off, using high-speed projectiles, beams, engineered rocks, whatever, and you might not see it until it hits. In that setting, revealing your exact location and your technological level may be a very bad move. If you assume there is at least some chance that other civilizations are hostile or just carelessly expansionist, then openly broadcasting your presence becomes risky. Staying quiet, minimizing your detectable footprint, and learning as much as you can before revealing anything becomes a rational strategy. In repeated game terms, silence and camouflage can be the dominant strategy in a relativistic universe where trust is hard, information is slow, and the cost of losing is extinction. Now look at the data we actually have. For decades, projects under the SETI umbrella have been listening for artificial radio or laser signals. We've pointed radio telescopes at nearby stars, at the galactic plane, at promising regions. So far, we have no confirmed detections of an artificial beacon. We've searched for Dyson spheres or other huge engineering projects by looking for stars with strange infrared excesses that might indicate waste heat from megastructures. Again, nothing conclusive. We're cataloguing more and more Earth-sized planets in habitable zones, but no unmistakable technosignature has turned up. One way to read that is, maybe we really are alone, or almost alone. Another way, consistent with the dark forest idea, is that advanced civilizations are out there, but hiding. They don't send easiest to spot narrowband radio beacons that scream "here we are" into the galaxy. They keep their communication tight, directional, encrypted, or they shift to technologies that look like noise against the background. They don't build giant, obvious megastructures that broadcast their existence. If they harvest star power, they do it in ways that don't stick out in our current surveys, or they manage their waste heat to blend in. That gives you a second layer of tension on top of the great filter. It's not just, can you survive natural and self-inflicted disasters? It's, can you survive in a neighborhood where revealing yourself might trigger someone else's paranoia? In that context, the SETI silence stops being purely bad news. It might be exactly what you'd expect if survival favours the civilizations that shut up. This loops straight into a very practical question. What should we be doing right now? Listening is one thing. Active SETI, sometimes called METI, messaging to extraterrestrial intelligence, is another. That means deliberately transmitting powerful signals outwards with content aimed at nearby stars saying we're here. Some scientists argue that we should do this, that after decades of listening it's time to speak. Others say that's dangerously naive because we have no idea who might be listening or how they think. From a dark forest perspective, broadcasting before you know the lay of the land is like turning on the flashlight and shouting in a dark, unknown forest where you know predators could exist. Maybe nobody's there, maybe friendly neighbours answer, or maybe something sees you first and decides not to take the risk of letting you grow. The point is, you don't get to assume good intentions. In game theory language, if just one significant player in the galaxy uses preemptively remove possible threats as their rule, and if preemption is easier than defending against unknown future tech, then being visible is a liability. We don't know if that's actually how things work out there. We have zero confirmed data on alien psychology, but we do know that the basic ingredients for dark forest logic are real, limited speed of light, vulnerability to long-range attacks, huge uncertainty about others' intentions, and no central authority to enforce peace. Those are enough to make stay quiet and hide your location a serious strategy, not just a sci-fi story. So you end up with a picture that is much darker than we're alone, and much more crowded than nobody exists. The galaxy could be full of civilizations, many older than us, each one aware that others could be out there, each one running its own risk calculations. They build, they explore locally, they monitor, but they do not shout. They minimize their beacons, manage their waste heat, and keep their presence as close to invisible as they can, because they've seen what happens to species that are loud and careless. Here is the final horror angle. The universe might be full of ancient, paranoid civilizations, each trapped in its own cone of silence, staring at the sky, seeing the same eerie quiet you see, and drawing the same conclusion, that speaking first might be fatal. Everyone is listening, no one is broadcasting, every civilization is hoping it's not already too visible, hoping nobody else has noticed it yet, hoping that caution will buy more time, and you right now are just starting to build the tools that could make you loud on a galactic scale, long before you really understand what kind of game you've walked into. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.